So good day. Our topic today is all about torque, or in your engineering majors, torque is also known as moment. So the main question we have to ask ourselves is, what is the cause of change in rotational motion? So we've been talking about angular velocity, angular acceleration. So my main question is, in the first place, why would a rotating object have an angular acceleration? What causes that for an object that is rotating, or a rigid body to be rotating, to suddenly have an increase or a decrease in its angular velocity? Well, the correct answer is the reason for a cause in a change in rotational motion, is because a torque is being applied to that object. So what is torque? Torque is what happens when you apply a force to a object that can rotate, and that force causes a change in angular velocity, or causes angular acceleration. So in this case, we have a door, and there's a hinge that attaches to the door, giving the door ability to rotate, no? Like all doors. You can achieve a more rapid rotation for the door by applying the force near the doorknob than by applying it near the hinges. So you may have experienced this if you push the door to open it closer to the hinges, then you need to apply more force, right? In order to achieve the same rapid rotation which you need to open the door. And it's much easier to make the door rotate if you apply the force farther away from the hinge, or actually in the doorknob. And that's why doorknobs are placed as far away from the hinges as possible, so that you apply minimum force for maximum rotation. So therefore, essentially, by applying force, you have accelerated the doorknob in terms of angular acceleration. You have changed the angular velocity of the doorknob from 0 to some angular velocity because you opened it, you made it rotate. So therefore, by applying a force to an object that can rotate, you can cause that object, or that rigid body, to have an angular acceleration. But it's not just about the force, because as you see here in this example, where you apply the force also matters, no? If you apply in with respect to its distance from the hinge, or the axis of rotation, same amount of force can have a different effect, can have a different, can produce different angular acceleration. So this torque is more than just the force. So actually, torque is the tendency of a force to rotate an object about some axis. Okay, so torque, it has something to do with the force, but it's not only that. No, torque also has something to do with where you apply the force, and also what direction you applied the force. Because imagine if, for example, we apply another force, C, but this is how you apply that force. C may be the same strength as B and A, but you won't be able to cause the door to rotate if you apply force C such that it is parallel to the door and passes through the hinge. The line of force passes through the axis of rotation. In that case, you may apply the same amount of force, but you won't be able to rotate the door. So this torque has something to do with the force. It has something to do with where you apply the force. And it also has something to do with the angle at which you apply the force. to the rotating object. So, you know, that's why we have another name for it. To make an object rotate or cause an angular acceleration, we need the concept of torque. And torque is represented by the symbol tau, right? And there is an arrow on top of tau, which implies that torque is a vector. But in order to get the magnitude, if we are only interested in the magnitude of the torque, this is the formula. So R here is the distance. R here is the distance from the axis of rotation to the point of application of the force. F is the force applied. And phi here is the angle between the R vector and the F vector. So in order to get the angle between the R vector and the F vector, you should connect both vectors to the tail and find that short angle. So phi here is the short angle between R and F. So for example, we have this one axis of rotation, this is the door, and you apply a force in this manner. R is actually a vector that starts at the hinge or the axis of rotation and points to where the force is applied. This is your R, okay? And so what is the angle between F and R? Well, usually this angle is given or this angle is given, which let's say this is angle alpha and this is angle beta. So angle alpha is measured from the y-axis and angle beta is measured from the x-axis. Which one is the correct angle? Which one is essentially phi, alpha or beta? Well, the way to figure out which angle is the correct angle is if you connect the force vector. Now we know that the force vector is northeast, and then you put the tail, you connect both tails of the position vector and the force vector. So this one, as you can see, this looks more like the beta angle, right? So in this case, the beta angle is the alpha. It's the phi angle in the formula. Okay. I hope that you understood that. Although there is another formula for torque, FD. So again, R is the distance between rotation axis and the point of application of force. And D here, this is known as the moment arm. So how do we find the moment arm? So this is another way of finding the torque, right? If you don't like this formula, you can use this formula, FD. D, the moment arm, this is perpendicular distance from the rotation axis to the line of action of force. So let's look at one example. So let's say this one. So this is the axis of rotation here. The axis of rotation, and this one, let's say this is the point of application of the force. And phi here, right? This is the y component of the force. You might be interested in that. And the x component of the force. You see the y component, it features in our formula, right? Can you see that it features in our first formula, RF sine theta? So F sine theta. So the y component of the force, provided that phi is measured, is the short angle between F and R. Here's our R, no? It is the position vector that starts at the axis of rotation and points at the point of application of the force. So where is D in this case? D is right here. So what is happening here? This one is the line of action of the force, no? So it extends all the way down and all the way up. It is the line where your force belongs to. So if we just extend the force vector, the original force vector, extend the line of the force vector, that is the line of action of the force. And we just want to find D, where D is perpendicular to that line of action. So there is only one line that is perpendicular to the line of action of force. That is this line here that starts from the hinge towards the line of action of force. That's your D, and this forms a right angle. And through geometry, you will find that phi here is phi is the same phi here because of the alternating interior angles theorem. And here you will find that D is one side of this right triangle where R is the hypotenuse. So we can say that, for example, sine phi is, that's phi is equal to opposite of phi, which is D over the hypotenuse, which is R. So therefore, D actually is just R sine phi in this case. So it's like going back to the first formula, no, R sine phi. That's one way to solve for the torque. You first figure out what the line of action of the force is and get that moment arm, which is perpendicular to the line of action of force, and use trigonometry to solve for what the value of D is. So D is known as the moment arm or the lever arm. So if there are two or more forces acting on a rigid object, each tends to produce rotation about the axis through O. So if this is the axis of rotation for this object, so notice that force 1, it will tend to make this rigid object rotate clockwise, right? Clockwise, correct. Yeah. No, counterclockwise pala. Yeah. F1 tends to make the rigid object rotate counterclockwise, while F2 tends to make the object rotate clockwise. And by definition, if a force tends to make an object rotate counterclockwise, then the torque that the force produces, it's positive. So if the torque is positive if the force that causes that torque tends to make the rigid object rotate counterclockwise. But if the force, like in this case, force 2, it tends to make the object rotate clockwise. So we, by description, by definition, may call that torque negative. Okay, so this is the formula. No? Torque 1 is positive, torque 2 is negative. Summation of torque is simply T1 minus T2 is equal to F1 D1 and F2 D2. Remember that these are the moment arms, no? As you can see, so this one is the line of action of force. Line of action of force for F1 is this one, right? And there's only one moment arm that forms a perpendicular line that is perpendicular to the line of action of force of F1, and let's call that D1. And for force 2, the line of action of force is this one. And there's only one line that is perpendicular to this line of action of force. And that is the line here, the D2 line. And D2 is the moment arm. Let's solve some problems. The body in the figure is pivoted. I can't seem to see the given because anyway, let me, there it is. So the body in the figure is pivoted at O, right? And two forces act on it as shown. If R1 is equal to 2.19 meters, R2 is equal to 2.53 meters. Force 1 is 5.68 newtons, force 2 is 5.9 newtons. Theta 1 is 72 degrees, and theta 2 is 49 degrees. What is the net torque about the pivot? The answer is 0.565 Newton meter. So the net torque is just the sum of all torques. So force 1 is causing the rigid object to rotate counterclockwise. Yeah, force 1 is causing the object to rotate counterclockwise, and force 2 is causing the object to rotate clockwise. So torque 1 is positive, torque 2 is negative. So let's look at torque 1. So we solve for torque 1, we solve for torque 2, and then we add torque 1 minus torque 2 because torque 2 is negative. So the formula is, let's use the second formula for this one. So let me just redraw the force vectors and the position vectors. So I have to, how do I start? How do I undo? Okay, there it is. And let's say that the this one is the force vector, right? This is F1. And this one here is theta 1. So actually, class, theta 1, this is the line of application of the force, right? And so we're looking for the moment arm. The moment arm is this is the, remember that the moment arm starts at the axis of rotation, and it's a line drawn towards the line of action of force. That this line is perpendicular to the line of action of force. So that's this one. This is the line that is perpendicular to the moment of action of force. I mean the line of action of force. So how do we solve for D1? Well, according to Tycho, this is also theta 1. No? So therefore D1 is actually the sine, right? R sine theta 1. Because if you just focus on this right triangle, let me use a different ink color and trace out the right triangle I'm referring to. This one, this is the right triangle I'm referring to. Clearly, D1 is opposite of the angle theta 1, and R is the hypotenuse. So D1 is R sine theta 1. And so, from our formula, T1 is equal to positive. This is positive, right? Because it causes the force 1 causes our rigid object to rotate counterclockwise. So positive F1 D1. So F1 D1 or F1 R1, this is R1 sine theta 1. Right, so about torque 2. So torque 2, we just redraw our this one is our R2, and this one is F2, right? And the theta is defined to be this one, theta 2 is defined to be that one. So let's draw the line of action of the force. This one is the line of action of the force. I'm just extending the force vector from the tail and from the head. So this is the line of action of force, right? So which line, starting from this one, starting from the axis of rotation, which line is perpendicular to the line of action of force? And there's only one line, and that is this line. This one is D2. And D2, that one is perpendicular to the line of action of force 2, D2. And again, using alternate interior angles theorem, this one is theta 2. And as you can see, if we focus on the right triangle that is formed, this one, we will find that sine of theta 2 is opposite over hypotenuse, D2 over R2. So therefore D2 is R2 sine theta t. But we have to remember that our T2 is negative, R2 negative, because it causes our rigid object to rotate clockwise. So the net torque, therefore, is T1 positive minus T2. Right? Well, T1 vector plus T2 vector, but T1 is F1 R1 sine theta 1, and our T2 vector has a negative sign, negative F2 R2 sine theta. F1 here is 5.68. Here we're substituting values, 5.68. Anyway, let me just solve this. Let me pause the recording and let me see if I got the same answer as what is found in the top above, 0.565. Okay, so that point, I got 0.5648, and that's correct, 5.56. So let's proceed to the next problem. So a small ball of mass 0.89 kilograms is attached to one end of a 1.4 meter long massless rod. So that's our R. Clearly that's our R, no? 1.4 meter long massless rod. And the other end of the rod is hung from a pivot. So this has to be our axis of rotation. When the resulting whoa, what happened? Why did this appear? When the resulting pendulum is 36 degrees from the vertical, okay, this pendulum is 30 degrees. Okay. So let's change color. Pendulum is 36 degrees from the vertical. So this has to be at 36 degrees, right? What is the magnitude of the torque about the pivot? So we are the only force, right? The only force acting on, we are focusing on the small ball, and clearly the small ball will rotate, right? Because it's a pendulum. So that swinging action is a form of rotation. There's only one force acting on the small ball, and that force is the force of gravity, right? So the weight of the small ball, which is mg, right? So the torque here is the torque that is produced by the force of gravity. So the formula there is Fg and times D, where D here is our moment arm. So how do we again find the moment arm? Well, here's the first step. We need to extend our line of action of force. So we draw dash line at the tip and at the head, right? So we just extend our force, gravitational force in this case. So we have this line of action of force. It's starting from the pivot, right? Starting here, where is that line that is perpendicular to the line of action of force? So if you haven't seen that already, that's this line. This line, this is the line of action. This is our D. So how do we solve for D? Well, if we just redraw the right triangle that we formed, this one is R, this one is D, right? So how do we solve for D? This one is 90 degrees. This one is 36 degrees. So therefore, if this one is 36 degrees, then this one is also 36 degrees. So I hope you remember that, no? I think it's, I don't know what the name of this geometric theorem is, but I think this one is the alternate interior angles theorem. I made a mistake previously. I mentioned the previous example, this one. I think this is the, I don't know what the name of this is. Anyway, what's important is we now know that this one is 36 degrees. So therefore, sine of 36 is, that's opposite over hypotenuse. So D is equal to R sine 36. Therefore, we can now solve for the torque produced by gravity. It's just the force of gravity times D, which is R sine 36. And is this positive or negative? Let's see, just analyze. So this pendulum will definitely swing counterclockwise. Yeah, counterclockwise. So therefore, this is positive. This torque is positive. So mg r sine 36. So all we need to do now is substitute values. M is 0.99, G is 9.8 or 9.81, R is 1.4 meters, right? Sine 36. So let me see if we got the correct answer. M is 0.99 times 0.99 times 9.8 times 1.4 times sine of 36. I get 7.98. So we got the correct answer. The unit of torque pala is Newton meter, right? Newton from force and meter from the position vector R. We have one more problem. We don't have one more problem. We just have two problems. I hope you learned something from this presentation. The most crucial will be how to draw the line of action of force, how to get the moment arm or the lever arm, which is the line that is perpendicular to the line of action of force, starting from the pivot, and how to use the torque formula. So that's the end of our presentation.